Hello, and welcome to Space for Sleep. Comets are not visitors from nowhere. They are survivors. A bright comet in the night sky can look like a ghostly accident, a pale smear of light, a tail stretched away from the sun, a thing that appears for a few weeks and then vanishes into dark again. But the object behind that display is not new. It is ancient. Most comet nuclei formed when the solar system was young, more than 4.5 billion years ago, from the icy leftovers of the same disk that made the planets. They spent almost all of their existence in cold storage, in the Kuiper Belt, the scattered disk, or the distant Oort Cloud, far from the heat of the sun, preserving material from the solar system's beginning. That is what makes comets scientifically powerful. They are beautiful, but they are also archival. A planet like Earth has been melted, differentiated, weathered, eroded, recycled, and biologically transformed. A comet has not. Its nucleus may be dark, fragile, porous, fractured, and repeatedly modified at the surface by sunlight, but deep inside it can still preserve chemical information from the early solar nebula, water ice, carbon dioxide, carbon monoxide, dust, silicates, organics, and molecules that help connect planetary science to the origin of life. Comets also refuse to behave like simple objects. They brighten unpredictably. They outburst. They fragment. Their tails disconnect. Some survive close passages to the sun. Others fall apart before reaching perihelion. Some return every few years, processed by repeated solar heating. Others arrive from the Oort Cloud on million-year orbits, entering the inner solar system perhaps for the first time. And a few are not native to the solar system at all. Since 2017, astronomers have identified interstellar objects passing through our planetary system, including the unusual 1I Oumuamua, the clearly comet-like 2I Borisov and 3I Atlas, discovered in 2025, the third confirmed interstellar object and the second clearly cometary one. So a comet is not only an icy wanderer. It is a test of solar system history, orbital dynamics, chemistry, planetary defense, and astrobiology. It is a small object with a long memory. To understand comets is to understand why the solar system still sends pieces of its beginning back toward the sun. The cultural history of comets matters because it explains why these objects occupied such a powerful place in human imagination. A planet repeats. Venus returns to the evening sky. Mars brightens and fades. Jupiter and Saturn move slowly along the zodiac in patterns that can be learned. The moon cycles predictably, but a great comet appears without warning to a society that has no orbital mechanics, no telescopes, and no concept of small icy bodies falling inward from the outer solar system. It looks like a tear in the order of the sky. That difference made comets psychologically different from planets. Planets were wandering stars, but still familiar. Comets were intrusions. Their shapes were not points but blazes, swords, brooms, torches, feathers, rivers of light. Their tails seemed to point toward Earth or away from it, depending on geometry, and their appearances often coincided, by chance, with wars, deaths, crop failures, dynastic changes, or epidemics. Human beings are pattern-seeking animals. When a rare object appears in the sky and something terrible happens on Earth soon after, memory ties the two together. Modern astronomy removed the omen but not the awe. In some ways, the scientific understanding is more powerful than the superstition. A comet is not a message about a king's death. It is a remnant of planetary formation. It has spent billions of years in darkness. Its tail is made not of fire, but of dust and ionized gas driven by sunlight and the solar wind. Its orbit may be shaped by Jupiter, Neptune, passing stars, and the gravitational tide of the Milky Way. Its molecules may have formed in the cold chemistry of the early solar nebula, or even earlier, in the molecular cloud from which the sun was born. The ancient fear was wrong about cause, but not wrong about significance. A great comet is significant. It is just significant for reasons deeper and older than the historical events people once attached to it. A comet is, at its core, a small, irregularly shaped body of ice, rock, and dust, a remnant from the formation of the solar system, typically ranging in size from roughly a few hundred meters to a few tens of kilometers across. The solid nucleus of the comet, the actual physical object, is invisible from Earth under most circumstances, too small and too dark to resolve or even detect at the distances from which we usually encounter comets. What we see when we see a comet in the sky is not the nucleus, but the coma and the tails, the vast, diffuse envelopes of gas and dust that surround the nucleus and trail behind it as it approaches the sun. The nucleus is a mixture of water ice, carbon dioxide ice, carbon monoxide ice, and a variety of other frozen volatile compounds, ammonia, methane, formaldehyde, hydrogen cyanide, and dozens of other species detected spectroscopically in the gas that sublimits from active comets, along with a significant proportion of refractory material, silicate minerals, carbonaceous compounds, and in some cases what appear to be complex organic molecules. The relative proportions of ice and rock vary from comet to comet, but a rough average composition might be roughly half ice by mass and half non-volatile solid material, though this varies considerably. The surface of a comet nucleus, directly imaged now for several comets by visiting spacecraft, is not the pristine, gleaming ice field that the word icy might suggest. Comet nuclei are among the darkest objects in the solar system, with albedos, reflectivities of only a few percent, darker than charcoal, dark enough that comet nuclei are extraordinarily difficult to detect in the outer solar system even with sensitive telescopes. The darkness comes from a layer of refractory organic material, sometimes called gunk or organic mantle, in more formal scientific language, that coats the surface as a result of the sublimation of ice, leaving behind the less volatile organic compounds in a progressively concentrated surface layer. The surface that spacecraft have directly imaged is a dark, complex landscape of cliffs, pits, boulders, smooth plains, and fractured terrain, geologically rich and in many cases actively evolving on timescales short enough to be observed in the weeks and months of a spacecraft's proximity. The physical scale difference between a comet nucleus and its visible display is one of the most surprising facts about comets. The nucleus may be only a few kilometers across, a small mountain by terrestrial standards. But when it becomes active, it can surround itself with a coma tens of thousands or hundreds of thousands of kilometers wide. A body small enough to hide inside a large city can create a glowing cloud larger than Earth. Its dust tail can stretch millions or tens of millions of kilometers through space. Its ion tail can reach even farther, shaped by the solar wind and magnetic fields rather than by the comet's own gravity. This is possible because gravity at the surface of a small comet nucleus is extremely weak. A human standing on such a surface would weigh almost nothing. Gas escaping from sublimating ice can lift dust grains and small particles easily. The nucleus does not need to be massive to create a vast display. It only needs to release material into sunlight. The comet's beauty is therefore mostly a temporary atmosphere and tail, not the solid body itself. That temporary nature is important. A comet loses mass every time it passes near the sun. Jets excavate pits. Cliffs collapse. Dust mantles build up. Fresh ice is exposed and then depleted. Some comets become dormant, their volatile rich surfaces sealed beneath insulating layers of dust. Some split into fragments. Some disappear completely. A comet is a preserved object, but once it enters the inner solar system, it also becomes a self-eroding object. Every apparition is a form of slow destruction. When a comet enters the inner solar system and approaches the Sun, solar radiation heats its surface. At a distance of a few astronomical units from the Sun, the surface temperature rises enough for the volatile ices, primarily water ice, which is the most abundant volatile in most comets, to sublimate, transitioning directly from solid to gas without passing through a liquid phase at the very low pressures prevailing at the comet's surface. This sublimation releases gas that expands outward from the surface at high velocity, dragging with it fine dust particles embedded in or near the ice. The expanding gas and dust form the coma, a roughly spherical cloud surrounding the nucleus that can grow to be larger than the Earth or even larger than the Sun in diameter, despite the nucleus being only a few kilometers across. Solar radiation pressure, the physical pressure exerted on matter by the stream of photons flowing outward from the Sun, and the solar wind, the stream of charged particles flowing outward from the Sun's corona, both act on the coma material. Because they push away from the Sun, they sweep the dust and gas from the coma into the comet's tails, which always point away from the Sun regardless of the direction the comet is actually moving. This means that when a comet is receding from the Sun after perihelion, its closest approach, it is traveling with its tail stretching out ahead of it in the direction of motion. There are typically two tails visible in a bright comet. The dust tail, composed of fine dust particles released from the surface, appears white or yellowish in photographs, reflecting sunlight, and curves gently away from the Sun following the slightly different orbital paths of the dust particles after their release from the nucleus. The ion tail, composed of ionized gas molecules, particularly carbon monoxide ions, appears blue in photographs, the result of fluorescence excited by solar ultraviolet, and points almost directly away from the Sun following the magnetic field lines of the solar wind. The ion tail is straighter than the dust tail and responds rapidly to changes in the solar wind, sometimes developing disconnection events where the tail appears to break away from the comet and a new one forms, the result of abrupt changes in the solar wind's magnetic field switching the attachment point of the field lines to the comet. A bright comet near perihelion is one of the most spectacular natural sights available to a sky observer, with tails sometimes extending tens of degrees across the sky, many times the apparent width of the full moon. The specific brightness of any given comet is notoriously difficult to predict because it depends on the composition and activity of the nucleus in ways that cannot be measured until the comet is already approaching. Comets are frequently described as the most unpredictable objects in the solar system. A bright, highly anticipated comet can fizzle if its surface proves less active than hoped, while a modest comet can suddenly outburst dramatically if a fresh patch of ice is exposed by surface activity or if the nucleus fragments. The existence of two main comet reservoirs tells us something important about the early solar system. The planets did not form in a calm, finished arrangement. The young solar system was crowded with planetesimals, small icy and rocky bodies forming, colliding, scattering, and being thrown into new orbits by the growing planets. Jupiter and Saturn were already massive gravitational engines. Uranus and Neptune shaped the outer disk. The region beyond the giant planets was filled with icy debris, far denser than the Kuiper Belt we see today. In modern dynamical models, many cometary bodies formed nearer the giant planets and were later scattered outward. Some were ejected from the solar system entirely, becoming interstellar objects wandering between stars. Some were thrown into the distant Oort Cloud, where the Sun's gravity still held them weakly, but where passing stars and galactic tides could later perturb them back inward. Others remained in the flattened trans-Neptunian region or in the scattered disk, becoming the source population for many short-period comets. This means that the Oort Cloud is not a place where comets simply formed in place as a quiet spherical shell. It is more likely a memory of early chaos, a population of leftover planetesimals thrown outward by the giant planets and then stored at the edge of the Sun's gravitational reach. The Kuiper Belt and scattered disk are different memories of the same formation era, colder, flatter, closer, still structured by Neptune's gravity. Comets are therefore not only primitive chemically, they are primitive dynamically. Their orbits preserve information about the violent rearrangement of the young solar system. The orbits of comets fall into two broad categories that reflect two very different reservoirs in the outer solar system. Long-period comets have orbital periods exceeding 200 years, with many having periods of thousands to millions of years. Some long-period comets are on what appear to be essentially parabolic orbits, so elongated that they are barely gravitationally bound to the solar system, arriving from the very farthest reaches of the Sun's gravitational influence. These comets originate in the Oort Cloud, a vast, roughly spherical shell of cometary nuclei surrounding the solar system at distances of several thousand to perhaps 100,000 astronomical units from the Sun, extending roughly a quarter to a third of the distance to the nearest star. The Oort Cloud is one of the least directly observed structures in astronomy. No individual Oort Cloud object has ever been directly detected because these objects are both far too distant and far too dark to image with current instruments. The Oort Cloud's existence is inferred from the orbital properties of the long-period comets that enter the inner solar system. Their nearly random arrival directions from all parts of the sky, and their nearly parabolic orbits, imply a source population distributed spherically around the solar system at very large distances. The Oort Cloud is thought to contain trillions of cometary nuclei, leftover planetesimals from the formation of the solar system, scattered to these enormous distances by gravitational interactions with the giant planets during the early solar system's turbulent dynamical history. Objects from the Oort Cloud are occasionally perturbed into the inner solar system by several mechanisms. Gravitational perturbations from passing stars, which can change the orbits of Oort Cloud objects enough to send them on trajectories that plunge toward the Sun, the galactic tide, the differential gravitational pull of the Milky Way's mass on different parts of the solar system, which slowly perturbs orbital parameters on million-year timescales, and the gravitational influence of giant molecular clouds that the solar system passes through or near on its journey around the galactic center. These perturbations can change an object's perihelion distance, the point of closest approach to the Sun, from its usual enormous value of tens of thousands of astronomical units to something much smaller, sometimes bringing it within the inner solar system on a roughly parabolic trajectory. The first time a previously dynamically unperturbed Oort Cloud object enters the inner solar system, it is what astronomers call a dynamically new comet, one that has never previously passed close to the Sun and has preserved, essentially perfectly, the volatile rich surface composition acquired during the solar system's formation. These comets are often brilliantly active at large distances from the Sun because highly volatile ices like carbon monoxide that sublime at lower temperatures than water ice are still present in abundance and active even at several astronomical units from the Sun. They can disappoint, however, as they approach perihelion. The sudden intense solar heating near the Sun can overwhelm a surface that has no experience of such conditions, causing the nucleus to fragment, outgas violently and irregularly, or even disintegrate entirely. Short-period comets, those with orbital periods of less than 200 years, are distributed differently from the long-period comets. Rather than arriving from all directions, they tend to have prograde orbits, orbiting the Sun in the same direction as the planets, and their orbital inclinations are concentrated near the plane of the solar system rather than isotropically distributed. These properties indicate a different source population, the Kuiper Belt and the scattered disk, which lie in the plane of the solar system beyond Neptune's orbit. The Kuiper Belt contains thousands of known objects and an estimated population of hundreds of thousands of objects larger than 100 kilometers in diameter, orbiting in a belt between roughly 30 and 50 astronomical units from the Sun. When orbital perturbations, usually from gravitational interactions with Neptune, place a Kuiper Belt object on a trajectory that brings it within the inner solar system, it becomes what is called a Jupiter family comet, named for the strong gravitational influence Jupiter exerts on their orbits. Jupiter family comets typically have periods of a few to 20 years and low orbital inclinations. They are generally darker, more processed, and less volatilely rich than dynamically new long-period comets, because they have made many previous passes near the Sun and have lost much of their original surface volatiles. Halley's Comet is the most famous periodic comet, and one of only a handful of short-period comets with a period longer than 20 years. Its period is about 75 to 76 years, and it is the only naked-eye visible short-period comet that returns within a human lifetime. Halley's is classified as a Halley-type comet, with periods between 20 and 200 years, and has a retrograde orbit, moving in the opposite direction to the planets, suggesting it may have originated in the outer Oort Cloud or scattered disk rather than the inner Kuiper Belt that feeds the Jupiter family comets. Halley's has been observed and recorded at every apparition since at least 240 BC, with reliable records extending to ancient China, Babylon, and Greece. The Bayeux Tapestry, created around 1070 AD to commemorate the Norman conquest of England, famously depicts the comet Halley apparition of 1066, with terrified observers pointing at it while Harold II looks on from his throne, one of the most widely reproduced astronomical images in medieval art. Spacecraft changed comet science because they replaced imagination with landscape. Before the first close flybys, a comet nucleus was mostly an inference. Astronomers could measure brightness, spectra, gas production, dust tails, orbital motion, and non-gravitational accelerations caused by jets. They could model what the nucleus had to be, but they could not see its cliffs, pits, boulders, layers, smooth plains, or active vents. They could not watch the surface change as the sun warmed it. They could not measure local gas directly or test the mechanical strength of the surface. The spacecraft era revealed that comet nuclei are not simple dirty snowballs and not simple icy rocks. They are dark, fragile, irregular, porous, chemically complex bodies with active geology driven by sublimation rather than by internal heat. Their landscapes are not static. A cliff on a comet can collapse when sunlight weakens it. A pit can grow as ice sublimates beneath the surface. Dust can migrate and rest in smooth deposits. Jets can emerge from fractures, pits, and exposed icy patches. The result is a world that is tiny, cold, and ancient, yet active on human timescales when it nears the sun. This is part of what made Rosetta so important. It did not merely fly past a comet. It accompanied one. It watched a nucleus wake up, become active, pass perihelion, and fade again. That temporal coverage made 67P a laboratory for comet evolution, not just a photograph target. The history of cometary science is a story of progressively more sophisticated observations peeling away layers of mystery, from the ancient terror of a sky omen to the modern understanding of a preserved fragment of the early solar system. The first scientific breakthrough came from the English mathematician Edmund Halley, who in 1705 applied the gravitational laws recently formulated by his friend Isaac Newton to historical records of bright comets. By calculating the orbits of the comets of 1531, 1607, and 1682, Halley recognized that all three had very similar orbital parameters. They appeared to be the same object returning at roughly 75 to 76-year intervals. He predicted the comet's return around 1758, and although he died in 1742 before seeing the prediction fulfilled, the comet appeared on schedule in December 1758, was named in his honor, and demonstrated beyond doubt that at least some comets were periodic visitors to the inner solar system, not transient atmospheric phenomena, as Aristotle had maintained, but genuine astronomical objects moving under the influence of gravity in predictable, elliptical orbits. This was a conceptual revolution. Comets were not signs from the heavens, but parts of the solar system, obeying the same physical laws as the planets. Their apparently erratic appearances were simply the consequence of very elongated orbits that brought them close to the Sun infrequently and briefly, invisible during the long portion of their orbit spent far from the Sun, and detectable only during the relatively brief passage through the inner solar system. The next major conceptual advance came in 1950, when the American astronomer Fred Whipple proposed what he called the dirty snowball model of the comet nucleus. Before Whipple's model, comets were widely thought to consist of loose swarms of individual solid particles, a gravel bank model, rather than solid bodies. Whipple proposed instead that a comet nucleus is a single solid object, a mixture of ice and dust, that sublimates when heated by the Sun, producing the observed gas and dust outflow from a specific nucleus rather than from a diffuse swarm. Whipple's model was initially controversial but proved correct. Direct imaging of Halley's nucleus by the Giotto spacecraft in 1986 confirmed that it was a solid, potato-shaped body a few kilometers across, with active jets emerging from specific vents on the sunlit surface. The Giotto mission in 1986 was the first spacecraft to directly image a comet nucleus. Part of a fleet of 5 international spacecraft, including 2 Soviet probes and 2 Japanese probes in addition to the European Giotto, sent to intercept Halley's comet at its 1986 apparition. Giotto made a daring close approach to within about 600 kilometers of the nucleus, flying through the inner coma and surviving, barely, to transmit images and scientific data. The images revealed a nucleus roughly 15 by 7 by 7 kilometers, dark as coal, an albedo of only about 4%, with 2 prominent jets of gas and dust erupting from specific active areas on the sunlit side. Spectroscopic instruments detected water, carbon dioxide, and a range of organic molecules in the coma, confirming the volatile rich composition Whipple's model had predicted and revealing a molecular complexity far greater than earlier observations had been able to characterize. The characterization of Halley's comet at its 1986 apparition marked the beginning of the modern era of comet exploration, in which physical visits to comets by spacecraft transformed the discipline from essentially remote sensing and theoretical work to something approaching genuine geological and geochemical investigation. The first detailed characterization of a comet nucleus by a purpose-built scientific mission came from the Deep Space One flyby of Comet Borrelly in 2001 and the Stardust mission to Comet Wild 2 in 2004. But the program that most dramatically advanced comet science was the Deep Impact mission in 2005 and the Rosetta mission from 2014 to 2016. Deep Impact consisted of 2 spacecraft, a flyby craft carrying cameras and spectrometers, and a relatively massive copper impactor, weighing about 370 kilograms, designed to slam into the nucleus of Comet Tempel 1 at about 10 kilometers per second and excavate a crater, exposing fresh subsurface material for analysis. The impact occurred on July 4, 2005, and produced a dramatically bright flash visible through Earth-based telescopes and cameras on the flyby craft. But the excavated crater itself was obscured from direct imaging by the enormous cloud of fine dust thrown up by the impact. which turned out to be far more extensive than models predicted, suggesting that the near-surface material of Tempel 1's nucleus is extraordinarily fine-grained and porous, almost powder-like in its physical properties. The ejecta cloud and the changes in Tempel 1's activity following the impact were studied by Deep Impact and subsequently by the Stardust spacecraft, which was redirected to Tempel 1 in a mission called Stardust Next in 2011 and succeeded in imaging the crater created by the Deep Impact impactor, confirming it as a large, shallow depression about 150 meters across, consistent with the expected outcome of a high-velocity impactor striking the very low-density surface material. Stardust's primary mission was to fly through the coma of Comet Wild 2 in 2004 and collect samples of comet dust, both from the Wild 2 coma and from the interstellar dust stream, in aerogel collectors that could capture particles without destroying them at the impact velocities involved, then return the samples to Earth in a sample return capsule. The capsule landed in the Utah desert in January 2006, delivering the first samples of cometary material, other than the fine-grained interplanetary dust particles that have been collected from Earth's stratosphere for decades, which include a cometary component to terrestrial laboratories. The analysis of Stardust's Wild 2 samples was in many ways startling. Scientists expected to find material characteristic of the cold outer solar system where comets form, fine-grained silicates of interstellar origin, organic-rich material processed under cold, reducing conditions. Instead, the samples contained a significant component of material that had apparently been processed at high temperatures, including crystalline silicates that form only above about 800 degrees Celsius, and material that includes olivine and pyroxene crystals whose composition and texture are more consistent with formation in the hot inner solar system than in the cold outer disk. This implied that material from the hot inner solar system was somehow transported to the cold outer disk during the early solar system's formation, incorporated into the cometary material as it assembled. This radial mixing of inner and outer solar system material in the cometary population has important implications for how the solar nebula was structured and mixed during planet formation. The Stardust samples also contained a range of organic compounds, including glycine, the simplest amino acid, detected in careful laboratory analysis in 2009, providing the first confirmed detection of an amino acid in a cometary sample. The detection of glycine, a molecule with direct biological relevance as one of the building blocks of proteins, in cometary material supported the hypothesis that comets have delivered biologically relevant organic molecules to the early Earth. The Rosetta mission, operated by the European Space Agency, was the most ambitious and most scientifically productive comet mission ever conducted, and its results from 2014 to 2016 at Comet 67P Churyumov-Gerasimenko transformed understanding of comet nuclei, their composition, and their origin. Rosetta was launched in March 2004 and spent 10 years making its way to Comet 67P through a complex series of gravity assists, 3 Earth flybys and 1 Mars flyby, before rendezvous with the comet in August 2014, when 67P was still far from the Sun, beyond the orbit of Jupiter, with minimal cometary activity. This early rendezvous, while the nucleus was still cold and largely inactive, gave Rosetta an extended opportunity to study the nucleus before cometary activity made orbital operations more difficult, and to accompany the comet through its full passage through perihelion and back out to the outer solar system. The nucleus of Comet 67P revealed by Rosetta's cameras was unlike anything previously imaged. Rather than the roughly ellipsoidal shape seen for Halley, Borrelly, Tempel 1, and Wild 2, 67P has a dramatically bilobate shape, 2 roughly spherical lobes connected by a narrow neck. giving it a profile often compared to a rubber duck. This bilobate shape is now understood to be common among comet nuclei, with many of the comets directly imaged showing similar double-lobed or contact binary configurations, suggesting that many comet nuclei formed through the low-velocity accretion of two smaller objects, a gentle landing of two subnuclei rather than a violent collision. The surface of 67P, mapped in detail by Rosetta's cameras over months of orbital observation, showed a diverse and geologically complex landscape. Smooth plains covered in fine dust, the MAAP regions, lay adjacent to rough, fractured cliff faces exposing layered internal structure. Circular, flat-floored pits interpreted as active sublimation features, sometimes called sinkholes, punctuated the smooth surface in some regions. Meter-scale boulders, both isolated and clustered, were scattered across various terrains. The Hather Cliff on the nucleus's smaller lobe stood several hundred meters tall in sections, with vertical to overhanging faces that would be dramatic features even on Earth. One of the most significant findings from Rosetta was the detection of large-scale layering within the nucleus, sequences of relatively uniform layers extending across both lobes of the nucleus, visible where erosion and outgassing had exposed internal cross-sections. These layers, typically a few meters thick, appear to record sequential episodes of accretion and processing during the nucleus's formation, suggesting that 67P built up by the gradual accumulation of material rather than through a single large accretion event. The properties of the nucleus material were striking in their extremity. The bulk density of 67P, measured precisely from Rosetta's orbital perturbations, is only about 533 kilograms per cubic meter, less than half the density of water, and far less than any rocky material. This extremely low density implies a porosity of roughly 70 to 80%. The nucleus is mostly empty space, a loosely consolidated aggregate of material with enormous amounts of internal void. This is not a solid, compact ice-rock mixture, but a very open, porous structure, more like a sponge or a very loosely packed snow bank than the solid, dirty snowball that earlier models envisioned. Rosetta also complicated the old language used for comets. The phrase dirty snowball is memorable, and it was historically useful. It replaced the older idea that comets were loose swarms of dust and rock. But after Rosetta, the phrase can be misleading if taken too literally. A comet nucleus is not a clean ball of ice with some dirt mixed in, and not even necessarily a compact dirty ice object. It can be an extremely porous aggregate, dark on the outside, with dust, organics, salts, ices, and minerals distributed in complex ways, and with an internal structure that may reflect gentle accretion from smaller building blocks. The bilobate shape of 67P especially matters. It looks like two bodies joined at a neck because it probably is the result of two lobes coming together at low speed. That suggests that at least some comet nuclei formed gently through the accumulation and contact of smaller icy bodies rather than through violent impacts that would have compacted or melted them. This gentle formation helps explain why comet nuclei can preserve fragile structure and high porosity over billions of years. Rosetta's measurements of organics also changed the emotional weight of comet chemistry. Organic molecules in a comet do not mean life. They do not even mean biology is likely, but they do mean that chemically rich carbon compounds form naturally in small icy bodies. The gap between organic chemistry and life remains enormous, but the raw inventory is not rare. Comets show that the early solar system contained complex chemistry before Earth had oceans, before biology, before cells, before DNA. The ingredients were present before the recipe was known. Rosetta's mass spectrometers analyzed the gas escaping from 67P in extraordinary detail, detecting over 400 distinct molecules in the comet's coma, including water, carbon dioxide, carbon monoxide, methanol, ammonia, sulfur dioxide, hydrogen sulfide, acetaldehyde, formamide, and a remarkable array of complex organic molecules including glycolaldehyde, the simplest sugar alcohol, and ethylene glycol. The specific combination of molecules detected and their relative abundances provided the most detailed snapshot of comet chemistry yet obtained, and revealed a composition both similar to and different from other comets previously studied in less detail, implying real diversity in cometary composition, reflecting the variety of conditions in the early solar system where different comets formed. One of Rosetta's findings that attracted enormous attention and some scientific controversy was the measurement of the deuterium to hydrogen ratio in 67P's water. Deuterium is a heavy isotope of hydrogen, a hydrogen nucleus with an extra neutron, and the deuterium to hydrogen ratio varies systematically in different environments in the solar system, providing a fingerprint of where and how water formed. Earth's water has a specific deuterium to hydrogen ratio, and if comets delivered a significant fraction of Earth's water, the comets responsible should have a similar ratio. Rosetta found that 67P's water has a deuterium to hydrogen ratio about 3 times higher than Earth's oceans, far too deuterium-rich to be the primary source of Earth's water if 67P is representative of Jupiter family comets broadly. This measurement suggested that Jupiter family comets cannot be the primary source of Earth's water, pointing instead to either Oort Cloud comets, which earlier measurements had found with deuterium ratios closer to Earth's, or to water-bearing asteroids, particularly carbonaceous chondrite asteroids, which have deuterium ratios very close to Earth's. The water origin question is not definitively resolved by a single comet measurement. 67P may not be representative of all Jupiter family comets, and the mix of sources that contributed to Earth's water during the heavy bombardment epoch is likely complex. But the Rosetta measurement was a genuinely important constraint, and it illustrates how a single, well-chosen scientific measurement on a specific comet can have implications reaching far beyond that particular object. Rosetta also carried the Halley lander, the first spacecraft ever to land on a comet nucleus, and Halley's story, while ultimately bittersweet, illustrated both the extraordinary achievement of cometary exploration and the persistent challenge of operating in environments as strange as a comet nucleus. Halley was designed to land on the nucleus of 67P using a combination of harpoons fired into the surface and ice screws driven from its landing gear, securing it against the extremely low gravity, roughly 1/10,000th of Earth's surface gravity, that would otherwise allow it to simply bounce off or float away with the slightest perturbation. On November 12, 2014, Halley separated from Rosetta and descended for about 7 hours to the surface of 67P. The harpoon system failed to fire, and the ice screws could not grip the unexpectedly hard surface, so Halley bounced twice before coming to rest on its side in a shadowed location, with its solar panels receiving far less sunlight than planned. It operated for about 60 hours on its primary battery before falling silent as the battery depleted. In those 60 hours, Halley managed to complete most of its planned science program, including drilling into the surface, though not as deep as planned due to the limited operation time, and measuring the mechanical and thermal properties of the surface material, the composition of gas in the near-surface environment, and the electromagnetic properties of the nucleus interior. The results confirmed the extremely porous, low-density character of the surface material, revealed a near-surface crust that was harder than expected, and detected a remarkable diversity of organic molecules in the material it sampled and analyzed. Halley fell silent in November 2014, was briefly revived in June and July 2015 when the comet's approach to the sun brought more sunlight to its solar panels, and then fell silent again permanently. Rosetta's cameras found Halley's final resting place in September 2016, just weeks before Rosetta itself ended its mission by descending to the surface of 67P, a deliberate, controlled impact that brought the mission to a close as the comet receded beyond the distance at which the solar panels could provide adequate power. Rosetta's controlled descent to the surface on September 30th, 2016, produced images of unprecedented resolution from the comet's surface, resolving features as small as 2 to 3 centimeters from just a few hundred meters altitude, before the spacecraft impacted at about 90 centimeters per second and contact was lost. The images transmitted in those final minutes showed a surface of extraordinary complexity at the smallest scales: pebbles, gravel, dust deposits, and features that spoke to an intricate history of sublimation, transport, and redeposition of material over the comet's many previous passages through the inner solar system. Comet 67P is far from the only comet that has been scientifically scrutinized in recent decades, and the diversity of the cometary population, revealed by photometric surveys, spectroscopic observations, and the cumulative results of multiple spacecraft visits, is now understood to be considerable. Some comets are compositionally unusual in ways that provide information about the specific local conditions in the solar nebula where they formed. Hyperactive comets, those releasing more water than the estimated ice-exposed surface area of their nuclei should be able to provide, are thought to contain significant amounts of water ice in the form of very small grains mixed with the dust of their inner coma, grains that sublimate far more efficiently than the nuclear surface. Comet Hale-Bopp, one of the brightest comets of the 20th century and visible to the naked eye for approximately 18 months from mid-1996 to late 1997, was such a comet, enormously active and spectacularly bright in part because of its large nucleus, estimated at about 60 kilometers, and in part because of its high intrinsic activity rate. Comet Hale-Bopp was discovered in July 1995 by two independent observers, Alan Hale in New Mexico and Thomas Bopp in Arizona, both on the same night, still about 7 astronomical units from the Sun, far beyond Jupiter's orbit, already showing unusual brightness for such a large heliocentric distance. Over the following months, and into 1996 and 1997, as it approached perihelion, Hale-Bopp developed into one of the most spectacular comets visible in the 20th century, bright enough to become one of the defining sky objects of its generation, showing 2 prominent tails, a white dust tail and a vivid blue ion tail, extending across tens of degrees of sky. It became one of the most widely observed comets in modern history. Spectroscopic observations of Hale-Bopp produced an extensive inventory of molecular species in the coma, including the first detection in a comet of several complex organic molecules, and confirmed the remarkable richness of cometary chemistry. Comet McNaught in 2007 was briefly the brightest comet in 40 years, exceptionally bright near perihelion and producing a spectacular fan-shaped dust tail with multiple striae, parallel curved bands of dust, visible to southern hemisphere observers in the weeks following perihelion. Its southern hemisphere display was extraordinary, with the fantail filling a quarter of the sky under dark conditions. Comet Neowise in 2020 was the first bright comet visible from the northern hemisphere since Hale-Bopp, appearing in the northern sky in July 2020 and remaining visible to the naked eye for several weeks, offering a widely observed and widely photographed celestial display at a time when many people were spending more time outdoors and more time paying attention to the sky than usual. Comet Suchinshin Atlas, which reached naked eye visibility in October 2024, was the most recently significant bright comet, providing southern hemisphere observers with good initial views before developing its dust tail and becoming visible globally. Each bright comet appears only once in any given generation's sky-watching experience, and the accumulation of photographic and spectroscopic data from each one adds incrementally to the portrait of cometary diversity. On the other end of the scale from these spectacular visitors are the sun-grazing comets. Comets with perihelia so small that they pass within a few solar radii of the sun's surface, or even skim through the corona itself. The Kreutz family of sun-grazers, named after the German astronomer Heinrich Kreutz, who studied several of them in the 19th century, are fragments of a large comet that disintegrated in the inner solar system perhaps a millennium ago, distributing its remnants into a family of related orbits. Hundreds of Kreutz sun-grazers have been discovered since the SOHO spacecraft began its continuous solar coronagraph observations in 1996, most of them tiny fragments only tens of meters across that do not survive their passage through the corona, evaporating completely and never emerging on the far side. Occasionally, a larger Kreutz fragment, several kilometers across, survives perihelion and emerges to be visible from Earth, though the extreme heating of the solar approach often leads to rapid disintegration in the days or weeks following perihelion. Beyond the bright, spectacular comets lies a more recently studied population that has transformed understanding of the boundary between comets and asteroids, the active asteroids, sometimes called main belt comets. Main belt comets are objects orbiting in the main asteroid belt between Mars and Jupiter that display cometary activity, dust tails, or comas, at or near perihelion. Before the first main belt comet was recognized in 1996, the asteroid belt and the cometary population were generally considered entirely separate reservoirs, with no overlap. Asteroids were rocky, inert objects formed in the inner solar system. Comets were icy objects from the outer solar system. Main belt comets challenged this clean separation. Being dynamically asteroidal, their orbits are consistent with origin in the asteroid belt rather than the outer solar system, but physically comet-like in their activity. The activity of main belt comets is thought to be driven by sublimating water ice just beneath the surface, ice that has been preserved in the asteroid's interior for the age of the solar system, protected by a thin insulating layer of dust and refractory material on the surface, and exposed to sublimation when an impact or thermal processing removes the surface covering. This discovery that water ice can persist in the asteroid belt, in objects that orbit relatively close to the Sun, significantly expands the potential reservoir of water-bearing material available to have delivered water to the early Earth through impacts. The asteroid-comet continuum has been further blurred by the discovery of centaurs, objects orbiting between Jupiter and Neptune, on unstable orbits that will eventually carry them either inward into the inner solar system, where they will become active as Jupiter family comets, or outward, where they may become Kuiper Belt objects again or be ejected from the solar system. Some centaurs show cometary activity at distances far too great for water ice to be sublimating. Their activity is thought to be driven by the sublimation of more volatile ices, like carbon monoxide and carbon dioxide, which sublime at the colder temperatures prevailing at centaur distances. 2060 Chiron, the first recognized centaur, discovered in 1977, shows a persistent coma and is thus classified as both an asteroid and a comet. The largest known trans-Neptunian objects, the Kuiper Belt objects including Pluto, Eris, Makemake, Haumea, and others, are in many ways giant cousins of the cometary nuclei, composed of similar mixtures of ice and rock, but far larger, and stabilized in orbits that do not bring them close enough to the Sun to produce significant cometary activity. They are, in a conceptual sense, comets that never left the outer solar system. The relationship between comets and meteor showers is one of the most accessible and visually beautiful connections between cometary science and everyday astronomical experience. When a comet passes through the inner solar system, it deposits a trail of dust along its orbit, fine particles ranging from millimeter-scale grains to sand grain-sized material, shed from the nucleus as gas sublimates, and carries dust away. These dust trails persist along the comet's orbit, gradually spreading and diffusing over time as the individual particles experience slightly different orbital perturbations. When Earth's orbit crosses a cometary dust trail, the particles strike Earth's upper atmosphere at high velocity, anywhere from 11 to 72 kilometers per second, depending on the geometry of the encounter, and ablate in streaks of light we call meteors or shooting stars. The particles are traveling in parallel, all moving in the same direction along the comet's orbit when they encounter Earth, which produces the visual effect that the meteors appear to diverge from a single point in the sky called the radiant, named after the constellation in which the radiant lies, and giving meteor showers their names. The Perseids, the most reliable and widely observed annual meteor shower, occur each year around mid-August when Earth passes through the trail of Comet Swift-Tuttle, a periodic comet with a period of about 130 years. At peak activity, observers can see several dozen to over 100 Perseid meteors per hour under dark skies, each one a fragment of Swift-Tuttle no larger than a pea burning up in a streak of light. The Leonids, occurring around mid-November and associated with Comet Tempel-Tuttle, are normally a modest shower producing perhaps 10 to 15 meteors per hour at peak, but they are periodically spectacular. When Earth passes through a particularly dense portion of the debris trail, fresh material deposited in recent perihelion passages, the shower can produce a meteor storm, with thousands of meteors per hour raining from the sky in an overwhelming display. Leonid storms occurred in 1833, 1866, 1966, and 1999 and 2001, with the 1966 storm producing an estimated tens of thousands of meteors per hour at its peak, essentially continuous meteors falling from the Leo radiant. So many that observers reported they appeared to rain from the sky. The Geminids in December are unusual among major meteor showers in being associated not with a known comet, but with an asteroid, 3200 Phaeton, which shows weak cometary activity near perihelion. Another example of the asteroid-comet continuum blurring the traditional categorization. The Geminids are now typically the strongest annual shower in terms of reliable meteor rate, producing over 100 meteors per hour under dark skies at peak, and their association with an asteroid rather than an obvious active comet has led some researchers to suggest that Phaeton may be a rock comet, a rocky asteroid with some sublimating volatile component, possibly sodium, or a dormant or extinct comet nucleus that has exhausted its volatiles and retains only its rocky skeleton. The impact of comets on Earth, both literally and on the composition of our planet, is a subject that has attracted increasing scientific attention over the past several decades, as the role of early bombardment in shaping Earth's volatile and organic chemical inventory has become clearer. During the period of heavy bombardment from roughly 4 to 3.8 billion years ago, the early Earth was struck by vastly more comets and asteroids than it is today, as the outer solar system's initially crowded population of planetesimals was being dynamically sorted by gravitational interactions with the giant planets. The material delivered by these impactors included water, in the form of water ice in both asteroids and comets, and a rich inventory of organic molecules, including amino acids, sugars, and nucleobases, the chemical building blocks of proteins and nucleic acids. Carbonaceous chondrite meteorites, the most chemically primitive meteorites known, and the type closest in composition to the solar system average, contain up to a few percent water by mass in the form of hydrated silicate minerals and several percent of organic carbon, including amino acids, hydroxy acids, polyols, and nucleobases. The Murchison meteorite, which fell in Australia in 1969 and has been extensively studied in the subsequent decades, contains over 90 different amino acids, including all 20 of the amino acids used in Earth's biology, plus many others not used by terrestrial life. Whether the specific inventory of amino acids found in Murchison or in comets like Wild 2 and 67P contributed meaningfully to the prebiotic chemistry that preceded life on Earth remains a genuinely open question, but the chemical richness of the extraterrestrial inventory is not in doubt. The question of Earth's water is more subtle than the simple phrase comets brought the oceans. For a long time, comets were natural candidates. They are icy. Earth has oceans. The early Earth was bombarded by small bodies. It seemed straightforward to imagine water-rich comets delivering the missing water after the planet formed. But isotope measurements complicated that picture. The deuterium to hydrogen ratio in Earth's oceans is a fingerprint, and many measured cometary waters do not match it. Rosetta's measurement of 67P was especially important because it found a D to H ratio more than 3 times Earth's ocean value, making that comet a poor match for being a major source of terrestrial water if it is representative of its class. Carbonaceous chondrite asteroids, by contrast, often have water-related isotopic ratios closer to Earth's and are now considered a stronger candidate source for much of Earth's water. This does not mean comets contributed nothing. The early solar system was a mixture, and delivery histories are complicated. Some cometary water may have arrived. Comets may have contributed important organic molecules even if they were not the dominant water source. But the clean old picture, icy comets filled Earth's oceans, is too simple. The more accurate picture is richer. Earth inherited some volatiles during its formation, received additional material from water-bearing asteroids, may have received some cometary contribution, and was shaped by impacts, outgassing, atmospheric loss, and geochemical cycling. Comets remain part of the story, but not the whole story. The delivery of water to the early Earth is perhaps the most practically important question about cometary and asteroidal impacts. Earth formed from rocky, volatile pore material in the inner solar system, and the amount of water present in the initial accretion may have been insufficient to produce Earth's current ocean mass. The additional water delivered by impacts during the heavy bombardment, primarily from water-bearing asteroids, given the deuterium constraint on cometary water mentioned earlier, may have been a significant contributor to the current inventory. But quantifying exactly how much water came from comets versus asteroids, and how much was outgassed from Earth's mantle versus delivered from space, is an active area of research with no definitive answer yet. What is clear is that the material delivered by comets and asteroids during the early bombardment, water, organics, and the energy of impacts themselves, shaped the early Earth in ways that may have been crucial to the eventual emergence of life. The ocean exists, in part, because of impacts. The organic chemistry that preceded life was enriched, in part, by impactor-delivered molecules. And the episodic sterilization of the surface by the largest impacts, while obviously destructive, may also have played a role in driving chemical evolution in the surviving protected niches and in distributing prebiotic chemistry broadly across the early ocean. The question of panspermia, whether life itself, rather than just the chemical building blocks of life, might be transported between solar system bodies on comets or meteorites, is more speculative but scientifically respectable. Some microorganisms can survive radiation and vacuum conditions that they might experience in space over short timescales, and there are plausible routes by which material could transfer between Mars and Earth on timescales short enough that some fraction of microorganisms might survive the journey. Whether life has actually transferred between bodies in the solar system is unknown, but it is not physically implausible. The impact of comets on Earth today is negligible. The rate of large impacts has declined dramatically since the heavy bombardment, and we live in a relatively quiet period of solar system history. The most recent globally significant cometary impact in the geological record is uncertain. The Chicxulub impactor that ended the non-avian dinosaurs 66 million years ago is generally classified as an asteroid based on its inferred composition, but some researchers have suggested it may have had a cometary origin. The Tunguska event in 1908, a major air burst over Siberia that flattened roughly 2,000 square kilometers of forest, was likely either a small asteroid or a cometary fragment a few tens of meters across. The frequency of large cometary impacts today is low, though not zero, and monitoring programs tracking the orbits of known comets and asteroids provide the earliest warning for any that might threaten Earth on timescales of decades. The 1994 collision of Comet Shoemaker-Levy 9 with Jupiter, the first time humans directly observed a collision between two solar system bodies in real time, was a dramatic reminder of how comet impacts continue to shape the solar system. Shoemaker-Levy 9 was captured by Jupiter's gravity in the early 1990s and was torn into a string of about 21 fragments by Jupiter's tidal forces during a close pass, producing a remarkable string of pearls appearance in telescope images before the fragments impacted Jupiter over the course of several days in July 1994. The impacts were visible from Earth through amateur telescopes, producing dark scars in Jupiter's atmosphere larger than Earth itself that persisted for months. The event was observed by virtually every major telescope on Earth and by the Galileo spacecraft en route to Jupiter, producing the first comprehensive dataset of a major solar system impact. Comets also matter for planetary defense, though the risk must be kept in perspective. Most near-Earth impact monitoring focuses on asteroids because they are more numerous among known near-Earth objects, and because their orbits can often be tracked over many years. Long-period comets are different. They can arrive from the outer solar system with little warning compared with asteroids whose orbits are already cataloged. Their speeds are often higher, and their orbits can be steeply inclined, making deflection more difficult if one were discovered on an impact trajectory. But the probability of a large long-period comet impact in any human lifetime is extremely low. The correct emotional response is not fear, it is monitoring. Better surveys, better orbit determination, and better impact modeling reduce uncertainty. The same instruments that make comet science richer also make the solar system safer to understand. There is a useful humility in this. A comet is not an omen, but it is still a reminder that Earth is part of a dynamic solar system. The sky is not a fixed ceiling. It is a moving environment of bodies on intersecting paths, most harmless, some scientifically precious, and a very small number potentially hazardous over long time scales. Long-period comets arriving from the Oort Cloud represent both a scientific opportunity, delivering pristine, barely processed material from the outer solar system for direct study, and a potential, if rare, hazard. The question of whether any known long-period comet could impact Earth on historical timescales is one that planetary defense organizations take seriously, and the detection of newly incoming long-period comets is a priority for sky survey programs. The discovery of interstellar objects changed comet science in a way that is easy to underestimate. For centuries, comets were understood as members of the solar system. Even long-period comets from the Oort Cloud belong to the Sun. They are weakly bound, but bound. Interstellar objects are different. They are planetesimals from other systems, ejected during the formation or later dynamical evolution of their own stars, drifting through the galaxy until they happen to pass through ours. They are samples of planetary formation elsewhere, delivered without us asking. 1I Oumuamua, discovered in 2017, was the first confirmed interstellar object. It was small, fast, elongated, or oddly shaped by its light curve, and did not show ordinary cometary activity despite a small non-gravitational acceleration. That combination made it famous and confusing. The most cautious interpretation is that it was natural but unfamiliar, a type of object shaped by processes we do not yet understand well because we had never seen one before. The artificial technology speculation attracted public attention, but it is not the mainstream scientific explanation. 2I Borisov, discovered in 2019, was more reassuring in one sense. It looked like a comet. It had a coma and a tail. It released gas and dust. Its chemistry was broadly comparable to solar system comets, though with interesting differences. Borisov showed that comet-like bodies form in other planetary systems and can be ejected into interstellar space. Then came 3I Atlas, discovered in 2025, the third confirmed interstellar object and another cometary visitor. NASA reported that it posed no threat to Earth, never came closer than about 1.8 astronomical units from our planet, and reached perihelion around October 30th, 2025, at about 1.4 astronomical units from the Sun. Its discovery made clear that the first two interstellar objects were not anomalies, but the beginning of a population we are only starting to sample. The importance of these objects is not only that they are rare, it is that they are comparative planetology at the smallest scale. A comet from another star system can reveal whether the chemistry of icy planetesimals elsewhere resembles ours, whether other protoplanetary disks build similar small bodies, and how efficiently planetary systems eject their leftovers into interstellar space. The discovery of Comet Borisov in 2019, the first confirmed interstellar comet, an object clearly coming from outside our solar system on a hyperbolic trajectory that no amount of solar system origin could explain, opened an entirely new chapter in cometary science. Borisov was detected by amateur astronomer Gennady Borisov in August 2019 and studied intensively in the following months as it passed through the inner solar system before heading back out into interstellar space. Spectroscopic observations revealed a composition broadly similar to solar system comets: water, carbon monoxide, and the usual organic molecules, suggesting that the cometary chemistry we see in our own solar system may be universal. That comets throughout the galaxy may share broadly similar compositions reflecting the universal abundances of elements and the common chemistry of cold molecular clouds where star formation occurs. Borisov was the second known interstellar visitor, following Oumuamua in 2017, a more enigmatic object that showed no cometary activity but displayed a non-gravitational acceleration inconsistent with radiation pressure from a rocky body, suggesting either it was a fragment of something unusual or possibly, in one controversial proposal, an artificial structure. Oumuamua's true nature remains disputed, with the most mainstream scientific interpretation being a naturally occurring object, possibly an unusual natural body shaped by volatile loss, a low-strength aggregate, or another unfamiliar type of planetesimal, rather than anything artificial. Whatever it was, its passage through the solar system was too brief for the kind of detailed characterization that would have resolved the ambiguity. The Vera Rubin Observatory, with its decade-long legacy survey of space and time beginning in the mid-2020s, is expected to discover vastly more interstellar objects than have been found previously, because its combination of wide field and sensitivity will catch objects fainter and faster than any previous sky survey. Some estimates suggest that Rubin could find interstellar objects regularly, perhaps even several per year, depending on the true population and brightness distribution, allowing the first statistical characterization of the interstellar object population and potentially providing samples of cometary material from other stellar systems. The future of comet science will be shaped by survey telescopes as much as by spacecraft. For most of history, comets were found one at a time, by human eyes or by photographic surveys. The modern sky is different. Automated surveys scan huge areas repeatedly, looking for anything that moves or changes. This is why new comets, asteroids, near-Earth objects, trans-Neptunian bodies, and interstellar candidates are increasingly discovered by systems built for time-domain astronomy rather than by individual visual observers. The Rubin Observatory is especially important here. Its legacy survey of space and time is designed to image the southern sky repeatedly for 10 years, finding changes, supernovae, variable stars, moving solar system objects, and faint objects that earlier surveys missed. For comet science, this means earlier discoveries, better orbital arcs, better warning for rare visitors, and a much larger inventory of small bodies. A comet discovered while still far from the sun can be watched as it wakes up. An interstellar object discovered early enough might be studied for months rather than weeks. A potentially hazardous long-period comet might be detected earlier in its inward path. Spacecraft will answer different questions. ESA and JAXA's Comet Interceptor, planned for launch in the late 2020s, is designed to wait for a suitable target, ideally a dynamically new long-period comet, or possibly an interstellar object if one becomes reachable, and then fly by it with multiple spacecraft, making a three-dimensional snapshot of a relatively pristine body. That mission concept is important because most previous comet missions visited short-period comets that had already been processed by many solar passages. A dynamically new comet would be closer to untouched early solar system material. Together, surveys and interceptors change the strategy. Surveys find the rare objects early. Spacecraft give them physical detail. The next major leap in comet science may come from combining both, discovering a pristine visitor in time to send instruments to meet it. There is something about comets that still speaks to something deeper than scientific curiosity, and that connection is not irrational. A comet is ancient in a way that is almost impossible to feel. A nucleus that formed in the outer solar system 4.5 billion years ago has spent almost all of its existence in darkness, cold enough to preserve molecules from the solar system's beginning. While Earth formed, while oceans appeared, while life began, while continents drifted, while dinosaurs lived and vanished, while humans learned to write and build telescopes, most comet nuclei remained far from the sun, quiet and almost unchanged. Then a small gravitational disturbance can change everything. A passing star, the galactic tide, or the slow pull of a planet can shift in orbit. A body that has been stored for billions of years begins falling inward. Sunlight strengthens. Carbon monoxide and carbon dioxide wake first, then water ice. Gas lifts dust. A coma forms. Tails grow. A dark nucleus becomes visible across interplanetary space, and for a few weeks or months, something older than Earth as a living world becomes part of the human sky. Ancient observers were wrong to treat comets as omens of human events, but they were not wrong to feel that a comet mattered. A comet is a messenger, not from gods, but from time. It carries chemistry from the beginning of the solar system. It carries evidence of how planets formed. It carries clues about water, organics, and the small bodies that shaped early Earth. It reminds us that the solar system is not only planets on stable paths, but also reservoirs of dark, icy debris still capable of returning to light. And the comets are still out there, in the Kuiper Belt and scattered disk, in the distant Oort Cloud, inferred from the orbits of long-period comets, perhaps holding trillions of nuclei too faint and too distant to see directly. In interstellar space, where ejected planetesimals from other stars drift between systems, most will never become bright. Most will never be seen. But some will fall inward, brighten, fragment, survive, or vanish. Some will be studied by telescopes. Some may one day be visited by spacecraft. And one of them, at some unknown date, will become the next great comet in a future sky. That is the quiet mystery of comets. They are small bodies with enormous histories. They are fragile, dark, icy, dusty, chemically rich, and old beyond ordinary imagination. They connect the night sky to the birth of the planets, the chemistry of water and organics, the history of impacts, and the possibility that the same ingredients that help prepare Earth for life are common in planetary systems everywhere. There is one more reason comets are powerful for a sleep-friendly science story. They move between categories. They are not planets, but they help build planets. They are not stars, but they become visible because of sunlight. They are not alive, but they carry organic chemistry. They are not weather, but their tails respond to the solar wind almost like flags in an invisible storm. They are not geological worlds in the ordinary sense, but they have cliffs, pits, collapses, layers, avalanches, and surfaces that change. This makes comets unusually good objects for understanding the solar system as a connected system. A molecule in a comet may have formed in a cold molecular cloud before the sun existed. That molecule may have been incorporated into the solar nebula, frozen into a planetesimal, stored in the outer solar system, released during a perihelion passage, studied by a spacecraft, and then interpreted by scientists trying to understand how Earth became habitable. A dust grain from a comet may travel along an orbit for centuries before striking Earth's atmosphere as a meteor in an annual shower. A fragment of an interstellar comet may carry chemistry from a star that formed before our sun. Comets are therefore not marginal objects. They sit at the junction of many stories: star formation, planet formation, water delivery, organic chemistry, meteor showers, planetary defense, interstellar exchange, and human sky watching. Their nuclei are small, but the scientific map around them is wide. That is why they deserve more than the old image of dirty snowballs. They are better understood as frozen archives with unstable surfaces, temporary atmospheres, and orbits that connect the deep cold to the inner light. There is another way to understand comets. They are laboratories of low gravity. On Earth, gravity dominates almost everything we intuitively understand about landscapes. Loose material falls downward. Hills slump, dust settles, rivers cut valleys. Atmospheres are held against planetary surfaces. On a comet, gravity is so weak that those instincts fail. A pebble tossed gently from the surface might escape entirely. Dust lifted by a gas jet can drift away into space. A cliff collapse does not behave like a landslide on Earth because the falling material is barely falling. A spacecraft can touch the surface and bounce for hours. This low gravity affects the entire evolution of the nucleus. It allows large boulders to sit in places that would be unstable on a planet. It allows fragile overhangs, pits, and dust deposits to persist in forms that look strange to human eyes. It means that sublimation, the transition of ice directly into gas, can be a major geological force. On Earth, wind, water, ice flow, and tectonics reshape landscapes. On a comet, sunlight heats volatile ices. Gas escapes through pores and fractures, and the surface weakens from below. A pit can form because buried ice disappears. A cliff can collapse because sublimation undercuts it. A smooth plane can be dust redeposited from elsewhere on the nucleus. This is why comet surfaces look both familiar and alien. They have cliffs, cracks, pits, plains, boulders, and layers. But the processes shaping them are not the processes that shape mountains or deserts on Earth. They are the processes of a cold, porous body briefly warmed by sunlight in near vacuum. The coma also behaves in ways that are difficult to imagine from ordinary atmospheres. It is not an atmosphere held in place by gravity. It is an escaping atmosphere, continuously generated and continuously lost. Gas molecules sublimated from the surface stream outward and are gradually photodissociated or ionized by solar ultraviolet radiation. Dust grains are accelerated by gas drag and then sorted by size, shape, and sensitivity to radiation pressure. The comet is therefore surrounded by a temporary, unbound envelope, a cloud that exists only because material is constantly leaving. This makes comet activity a balance between exposure and insulation. Fresh ice exposed at the surface can produce jets. But as ice sublimates, dust and refractory material can accumulate, forming an insulating mantle. That mantle can suppress activity until cracks, impacts, collapses, or seasonal heating expose new volatile rich material. Comets can therefore turn on and off in irregular ways. A region that was quiet during one rotation may become active later. A comet that looked disappointing for weeks may suddenly brighten if a new vent opens or a fragment exposes fresh ice. This unpredictability is not a failure of astronomy. It is a real property of the objects. Comets are not smooth balls with uniform surfaces. They are patchy, layered, fractured, rotating, irregular bodies with local geology. Predicting the brightness of a comet means predicting how sunlight will interact with a surface we usually cannot see in detail over a nucleus whose activity history may be unique. That is why comet brightness forecasts are famously uncertain. The tails of comets are also more than visual decoration. They are diagnostics of the space environment. The dust tail tells a story about grain sizes and radiation pressure. Small grains are pushed more strongly by sunlight and spread differently from larger grains. The broad, curved dust tail of a bright comet is therefore a visible record of particles released at different times, moving along slightly different trajectories. The striations sometimes seen in great dust tails, narrow bands, or rays within the broader tail, can reflect waves of dust release, fragmentation of grains, or sorting by radiation pressure and orbital dynamics. The ion tail tells a different story. It is made of charged molecules interacting with the solar wind. Because ions follow magnetic field lines carried outward from the sun, the ion tail can react quickly to changes in the solar wind. It can kink, twist, brighten, or disconnect. A disconnection event happens when changing magnetic conditions effectively sever the old ion tail and a new one forms. In photographs, the effect can look dramatic. A blue tail broken away from the comet, drifting behind as a fresh tail begins to grow. A comet's tail is therefore a natural probe of the heliosphere. Long before spacecraft measured the solar wind directly, comet tails had already suggested that something was flowing outward from the sun. The fact that tails point away from the sun, regardless of the direction of comet motion, demanded explanation. The answer is that sunlight and solar plasma exert forces. A comet shows those forces in visible form. This makes every bright comet both an object and an instrument. It is a body being studied, and at the same time a tracer of invisible solar influence. The chemistry of cometary ices is one of the richest parts of the subject. Water ice is usually the dominant volatile near the sun, but it is not the only one. Carbon monoxide and carbon dioxide can drive activity at larger distances, where water ice is still too cold to sublimate efficiently. This is why some comets become active beyond the orbit of Jupiter or Saturn. Their surfaces are not being heated enough for water to dominate, but more volatile compounds can still escape. These volatiles give astronomers clues about where the comet formed and how much processing it has experienced. Ammonia, methane, methanol, formaldehyde, hydrogen cyanide, hydrogen sulfide, sulfur dioxide, formamide, acetaldehyde, and many other molecules have been detected in cometary comae. Some are simple. Some are chemically important for prebiotic chemistry. Some are fragile and preserve information about cold formation environments. The relative abundances vary between comets, which tells us that comets did not all form from a perfectly mixed reservoir. The early solar system had chemical gradients, temperature gradients, and local histories. Dust is equally informative. It contains silicates, carbonaceous material, organics, and sometimes crystalline minerals that require high temperatures to form. The presence of high-temperature minerals in comets is one of the strongest pieces of evidence that the early solar nebula was not a simple quiet disk where material stayed near where it formed. Material from the hot inner regions must have been transported outward and incorporated into icy bodies. Comets therefore preserve both cold and hot histories at once. Ices from the outer disk and mineral grains processed closer to the young sun. That mixture matters because it links comets to planet formation. Planets did not assemble from pure local ingredients. The disk was turbulent, evolving, mixing, and transporting material across enormous distances. A grain formed near the young sun could end up inside a comet beyond Neptune. A volatile molecule formed in a cold outer region could later fall inward and become part of Earth's impact history. The solar system was chemically connected from the beginning. There is also a distinction between primitive and pristine that is worth making. Comets are often called pristine, but no comet surface is completely untouched. Cosmic rays alter the outer layers over long times. Solar heating modifies surfaces during perihelion passages. Impacts, fragmentation, and outgassing reshape nuclei. Even in the outer solar system, radiation chemistry can transform ices and organics. A comet is not a perfectly sealed sample tube from the birth of the solar system. But compared with planets, comets are still primitive. They have not been globally melted. They have not undergone plate tectonics. They have not been weathered by oceans or atmospheres for billions of years. Their interiors can preserve early material far better than the surfaces of terrestrial planets. The task of comet science is to distinguish what is original from what has been modified, to read the archive while understanding the smudges on the pages. This is why sample return matters so much. Remote spectroscopy can identify gases and some dust properties. Spacecraft flybys can image surfaces and measure local environments. But laboratory analysis on Earth is still far more sensitive than most spacecraft instruments. A return sample can be studied with mass spectrometers, microscopes, isotope systems, and techniques that may not even exist at the time the sample is collected. Stardust, while 2 grains were tiny, captured at high speed, and altered by collection in aerogel, but they still transformed comet science. A future cryogenic sample return, one that preserves volatile ices as well as dust, would be even more powerful because it could bring back the delicate molecules that are usually lost or altered. Such a mission would be difficult. Comet surfaces are fragile. Volatiles must be kept cold. Contamination must be controlled. The sample must represent known context on the nucleus. But scientifically, the reward would be enormous. A direct laboratory inventory of ice, dust, organics, isotopes, and minerals from a small body formed at the edge of the planetary system. The line between comets and asteroids becomes more blurred the more carefully we look. The old picture was simple. Asteroids are rocky and live mostly between Mars and Jupiter. Comets are icy and come from beyond Neptune or the Oort Cloud. This distinction is useful but incomplete. Some asteroids contain hydrated minerals and water-related chemistry. Some objects in asteroidal orbits show comet-like activity. Some comets become dormant and look like asteroids after losing accessible volatiles. Some centaurs behave partly like comets, even at large distances. Some near-Earth objects may be extinct comet nuclei. The solar system does not organize itself according to human categories. It contains a continuum of small bodies with different ice fractions, dust content, histories, orbits, and surface states. The category comet usually describes behavior, the development of a coma and tail, as much as origin. An object can be dynamically asteroidal, but physically active. It can be dynamically cometary, but temporarily dormant. It can be icy inside and dark outside. It can look inert until sunlight or impact exposes buried volatile material. This continuum matters for Earth's history because the delivery of water and organics did not depend on neat labels. Early Earth was struck by a mixture of objects: carbonaceous asteroids, icy planetesimals, cometary bodies, fragments from different reservoirs. The chemistry delivered to Earth came from the population of small bodies as a whole, not from a single clean class. Meteor showers are one of the most direct ways ordinary observers encounter cometary material. A meteor in a shower is usually not a falling star and not a large rock. It is often a tiny grain, sometimes no larger than sand, moving so quickly that it compresses and heats the air ahead of it, producing a luminous trail. That grain may have been released by a comet centuries ago. It may have orbited the sun many times as part of a stream. Then Earth crosses the stream, and the grain's long, independent journey ends in a second of light. This gives meteor showers a strange intimacy. The Perseids are not only an annual spectacle, they are pieces of comet-swift Tuttle meeting Earth's atmosphere. The Leonids are pieces of Temple Tuttle. The Orionids and Eta Aquariids are debris from Halley's comet. When someone watches a meteor shower, they are watching comet dust enter Earth's atmosphere in real time. The parent comet may be far away, invisible, not due back for decades, but its trail continues to intersect Earth's path. Meteor storms are reminders that these trails are structured. They are not uniform rings of dust evenly spread along an orbit. Fresh trails can remain dense, and Earth's passage through one can produce thousands of meteors per hour. The Leonid storms of the 19th and 20th centuries were overwhelming because Earth crossed particularly dense debris streams. A meteor shower is therefore a map of past comet activity written across Earth's sky. Comets also teach patience because their timescales are so varied. A jet can change within hours. A nucleus can rotate in hours or days. An outburst can happen suddenly. A meteor shower can peak in one night. A periodic comet can return every few years. Halley's comet returns in about 76 years, long enough that many people see it at most once. A long-period comet may take thousands or millions of years. An Oort Cloud comet may be making its first inward journey since the solar system formed. Interstellar objects may never return to any star at all. This range of timescales gives comets their narrative power. They are dynamic in the moment and ancient in origin. They can change while we watch, yet their material may be older than every rock on Earth's surface. Bright comets also have a special place in modern sky culture because they remain unpredictable shared events. Most astronomical events can be forecast with great precision. Eclipses, conjunctions, meteor shower peaks, planetary oppositions. Comets can be forecast in position, but not always in beauty. The orbit can tell us where the comet will be. It cannot fully tell us how much dust it will produce, whether it will fragment, how its forward scattering geometry will affect its brightness, or whether it will become a great comet or a binocular smudge. That uncertainty makes anticipation part of the experience. Comet C 2023 A3 Suchinshin Atlas illustrated this. Before perihelion, predictions varied and some analyses warned that it might underperform or even fragment. It survived and produced a memorable 2024 display, becoming one of the most widely photographed comets of the decade. NASA noted that updated orbital solutions suggested its path after the encounter might take it out of the solar system altogether. That alone is remarkable. A comet visible to human eyes for a short time may be on a path that never brings it back. There is a final scientific humility in all of this. Comets are often described as time capsules, and that is true, but no time capsule opens itself easily. The archive is mixed, altered, layered, dark, fragile, and incomplete. A gas measured in the coma may come from surface ice, subsurface ice, distributed icy grains, or chemical breakdown of larger molecules. A dust grain may have formed in the inner solar system and been transported outward. A D to H ratio measured in one comet may not represent every comet. A nucleus surface may be processed while the interior remains primitive. Every result must be interpreted through models. That does not make comet science weak. It makes it real. The objects are complicated because the early solar system was complicated. A simple answer would be suspicious. The complexity is the message. The story of comets also includes disappearance. A comet can be discovered, named, followed for months, and then vanish in a way that feels almost personal to observers. Sometimes the disappearance is ordinary. The comet recedes from the sun, its activity fades, and it becomes too faint for telescopes. Sometimes it is more dramatic. The nucleus fragments. Activity drops suddenly. A brightening prediction collapses. A sun grazer enters the corona and never emerges. A comet expected to become spectacular becomes a cloud of debris. This vulnerability is not incidental. A comet nucleus is small and weak. Its tensile strength can be very low. It may be a loosely consolidated aggregate held together by self-gravity, cohesion, and history rather than by the strength of solid rock. When solar heating increases, volatile pressure builds in cracks and pores. Rotational stresses can increase if jets act like tiny thrusters. Tidal forces can become important during close passages by the sun or a giant planet. A comet is often one stress away from splitting. Fragmentation can create beauty and science at the same time. A split nucleus exposes fresh interior material, sometimes causing a sudden brightening as new ice sublimates. Multiple fragments can move together along similar orbits, revealing the structure of the original body. The Kreutz sungrazers are likely the descendants of a much larger comet that broke apart centuries ago, each fragment becoming a separate comet on a similar path. Shoemaker-Levy 9, torn apart by Jupiter, became a string of fragments before impact. A single comet can become a family. Disappearance also teaches caution. Comet ISON, discovered in 2012 and widely discussed as a possible spectacular comet for 2013, approached the Sun as a sun grazer and was largely destroyed near perihelion. For the public, it was a disappointment. For scientists, it was data, a demonstration of how intense solar heating and tidal stresses can disrupt a fragile nucleus. Comets do not owe observers a display. They follow physics, and sometimes the physics ends in dust. The same fragility makes comet nuclei scientifically honest. They are not polished monuments. They are temporary survivors of a violent formation history, stored in cold regions but not invulnerable. Their eventual destruction is part of the solar system's recycling. Dust released by comets becomes meteor streams, zodiacal dust, micrometeorites, and interplanetary material. Some of it falls to Earth. Some is blown away. Some remains in orbit for thousands of years. The comet changes form, but its material continues participating in the solar system. The zodiacal light is one subtle example of this continuing presence. Under very dark skies, after sunset or before dawn, a faint triangular glow can sometimes be seen extending upward from the horizon along the plane of the solar system. This is zodiacal light, sunlight scattered by countless tiny dust particles orbiting the sun. Much of that dust comes from asteroid collisions and comet activity. It is not the glow of a single object, but of a diffuse disk of debris, a quiet reminder that the solar system is filled with fine material shed by small bodies. A comet tail is spectacular because it concentrates dust in a visible stream. The zodiacal cloud is quieter, spread through the inner solar system, but it is part of the same larger process. Small bodies shed material. Sunlight reveals it. Dust slowly spirals inward under pointing Robertson drag, collides, fragments, or is swept up by planets. The solar system is not clean. It is dusty, and comets are one source of that dust. There is a connection here to spacecraft as well. Interplanetary probes travel through an environment containing dust grains moving at high speeds. Most grains are tiny, but at spacecraft velocities, even tiny particles matter. Missions to comets must be designed to survive dust impacts, gas drag, uncertain surface conditions, and low gravity. Giotto's dangerous flyby of Halley's comet, Stardust's aerogel capture of wild 2 particles, and Rosetta's careful navigation around 67P all required engineering built around the physical reality that comets are active, dusty, and unpredictable. Comets also invite us to think about scale in a different way from planets. A planet is large enough to become round under its own gravity. It can have layers, internal heat, atmosphere, weather, and geology on a global scale. A comet is too small for that. It is irregular, often only kilometers wide, with gravity too weak to force a sphere. And yet, because it carries volatile ice, it can create phenomena on planetary scale. A coma larger than Earth, a tail longer than the distance to the Moon, a dust trail that intersects Earth's orbit every year for centuries. This contrast is one of the most elegant facts about comets. The solid body is small. The visible effect is huge. The nucleus is hidden. The coma is enormous. The object is dark. The tail glows. The body has almost no gravity, yet its orbit can be controlled by the largest planets and disturbed by the galaxy. The comet is physically modest and dynamically grand. This is why comets often feel more dramatic than their size suggests. A mountain-sized object can become a sky-spanning phenomenon. A fragment from the outer solar system can enter human history. A body too dark to see at distance can become visible to millions of people because sunlight turns its surface chemistry into atmosphere and tail. There is another subtlety in comet tails. They do not trail behind the comet the way smoke trails behind a moving train. This is a common misconception because the word tail suggests motion. But comet tails point away from the sun, not necessarily opposite the comet's direction of travel. Before perihelion, the tail may appear behind the comet along its path. After perihelion, when the comet moves outward, the tail can point ahead of it. The tail is not awake through space. It is material pushed by sunlight and solar wind away from the sun. Understanding that one fact changes the visual meaning of a comet. The tail is not showing where the comet has been. It is showing where the sun is. It is a visible arrow of solar influence. A comet in the sky is therefore also a diagram. Nucleus here, sun in the opposite direction, dust and ions being shaped by forces that are normally invisible. Comets also remind us that the solar system has memory in multiple forms. The planets remember through craters, isotopes, atmospheres, and geological layers. Asteroids remember through mineralogy and impact history. Meteorites remember through chondrules, inclusions, and radiometric ages. Comets remember through ices and organics, through fragile minerals, through isotopic ratios, through orbits that point toward reservoirs we cannot directly see. No single type of object preserves the whole story. The early solar system must be reconstructed from many partial archives. This is why comet science is connected to meteorites, asteroid missions, lunar samples, Mars geology, and exoplanet formation. The question is not only what comets are, it is how small bodies record the conditions under which planets form. If we understand comets, we understand one major reservoir of leftover planetary material. If we understand asteroids, we understand another. If we compare both, we begin to see the mixing, heating, delivery, and scattering that built the terrestrial planets and shaped their volatile inventories. The amino acids and organics found in cometary material should be handled with both excitement and restraint. Glycine in stardust samples and glycine detected by Rosetta at 67P are important because they show that biologically relevant molecules can form or survive in cometary environments. But amino acids are not life. They are building blocks, not organisms. The gap between glycine and a living cell is vast. Comets can deliver ingredients. They do not deliver biology by default. Still, ingredients matter. Prebiotic chemistry depends on available molecules, energy sources, environments where reactions can concentrate and cycle in time. Early Earth was not working with a blank chemical slate. It received extraterrestrial organics from meteorites, asteroids, interplanetary dust, and likely comets. That delivery did not create life by itself, but it may have enriched the chemical inventory from which life emerged. This is the careful middle position. Comets probably did not bring life to Earth in any simple sense. They may not have brought most of Earth's water, but they did carry water, carbon compounds, and complex molecules into the inner solar system. And those deliveries were part of the environmental and chemical background in which life began. The possibility of panspermia, life traveling between worlds, remains separate from the more modest and better supported idea of chemical delivery. It is physically possible for rocks blasted off Mars to reach Earth. We know Martian meteorites exist. It is plausible that some microorganisms, if shielded inside rock and transferred quickly enough, could survive parts of such a journey. But interstellar panspermia or comet-delivered living cells is far more speculative. Space is cold, irradiated, and long. Survival over millions of years is difficult. The idea is not impossible in every form, but it is not needed to explain life's origin on Earth and should not be treated as established. Comets, then, are best understood not as life carriers, but as chemistry carriers. That is already profound enough. They also connect to the question of how common similar chemistry might be in other planetary systems. If 2I Borisov and 3I Atlas are broadly comet-like, and if future interstellar objects show similar volatile and dust chemistry, then cometary chemistry may be a common outcome of planet formation. Young stars with protoplanetary disks should naturally make icy planetesimals beyond snow lines. Giant planets and planetary migration should naturally eject some of them. Interstellar space may be filled with frozen fragments of planetary systems, each carrying chemical records of its birth environment. In that sense, comets may be universal small fossils of planet formation. We happen to see the ones formed around our sun most often, but the galaxy may contain enormous numbers of them, drifting silently between stars. This gives the search for interstellar comets a deeper meaning. Each one is a comparison point. Does it have water? Carbon monoxide? Carbon dioxide? Dust like ours? Unusual isotope ratios? Does it behave like a dynamically new Oort Cloud comet, or like something stranger? The answers will tell us whether our solar system's small body chemistry is typical or unusual. The next decades may change this field rapidly. Rubin will find more moving objects. Comet Interceptor may visit a relatively pristine comet. Larger telescopes will study faint activity at greater distances. Laboratory techniques will keep improving. Old stardust grains and interplanetary dust particles will be reanalyzed with instruments more sensitive than those available when they were collected. The archive grows not only when new samples arrive, but when old samples are read with better tools. That is a useful thought for a subject built around ancient objects. Sometimes the future of discovery lies inside material already in our possession, waiting for better questions. Comets have another role in human experience because they create shared sky events that do not belong to any one nation, instrument, or observatory. A total solar eclipse follows a narrow path. A planetary mission belongs to agencies and instruments. But a bright comet, if geometry allows, can be seen by anyone under a dark enough sky. It belongs to the public in a rare way. People photograph it over cities, deserts, mountains, oceans, ruins, observatories, and backyards. It becomes part of human memory not because it changes Earth, but because it appears above Earth, briefly connecting everyday life with deep time. This public quality matters. Comets helped pull astronomy into culture long before telescopes existed, and they still do. A child seeing a comet may not know about Rosetta, D to H ratios, the Kuiper Belt, or Oort Cloud perturbations. But the visual experience can become the doorway to those ideas. The streak in the sky leads to questions. The questions lead to science. That is perhaps the best reason to keep telling the story of comets carefully. They are accessible enough to inspire, complicated enough to teach, and ancient enough to make the solar system feel historical rather than static. There is one final distinction that helps make comets clearer. A comet is not defined by where it is, but by what it does when sunlight reaches it. Far from the sun, a comet nucleus may look almost identical to a dark asteroid, small, faint, inert, and unresolved. Its cometary nature becomes visible only when heat activates volatile ices and creates a coma. In that sense, a comet is partly a behavior. It is an icy small body capable of becoming active. A dormant comet can hide among asteroids. An active asteroid can briefly behave like a comet. The categories are useful, but nature is more gradual than the names. This matters because the same object can pass through different identities over time. A young comet entering the inner solar system for the first time may be volatile rich and active at large distances. After many returns, its surface may become insulated and depleted. Eventually, it may appear almost asteroidal, a dark remnant with only occasional weak activity. It may fragment, become a meteor stream, or be ejected after gravitational encounters. A comet is not a permanent state. It is a phase in the long life of a small body. Even the word ancient needs care. A comet's material may be ancient, but its current surface can be young. A cliff collapse last year can expose fresh ice from a nucleus that formed billions of years ago. A dust layer can be redeposited during one perihelion passage. A pit can open over a few months. The comet is ancient and current at once, old in composition, active in surface evolution. This is what gives comet science its unusual texture. It is archaeology combined with weather. It is deep time combined with changing surfaces. It is chemistry from the solar system's birth expressed through jets that can vary from one rotation to the next. The next time a bright comet appears in the sky, the most important thing to remember is that the visible object is temporary. The tail will fade. The coma will disperse. The nucleus will return to darkness or break apart. But the material behind that brief display has endured almost since the sun was born. A human lifetime may contain only a few truly memorable comets, but the cometary reservoirs have been feeding the inner solar system for billions of years. The night sky makes comets look like interruptions. Science reveals them as continuity. A comet also changes how we think about distance. The outer solar system is usually imagined as empty, but comets show that emptiness is populated by cold remnants. Beyond Neptune, icy bodies move in darkness, some stable for billions of years, some gradually perturbed into new paths. Farther out, the Oort Cloud is not a bright structure but a statistical presence, a vast reservoir inferred from returning messengers. We do not see the reservoir directly. We see the consequences of its existence when one nucleus arrives near the Sun. That makes every long-period comet a kind of sample from an invisible region. Its orbit points backward to a place too distant to image. Its chemistry points backward to the conditions of formation. Its activity points forward to what sunlight does to untouched or lightly processed ice. One object, properly studied, connects the unobservable outer boundary of the solar system to telescopes on Earth and instruments in space. There is also a lesson in modesty. The solar system was not built only from the large things we name first. The sun, planets, and moons dominate the picture because they are large and familiar. But small bodies carry a disproportionate amount of historical information. Comets, asteroids, meteorites, interplanetary dust, Kuiper Belt objects, and centaurs are the leftover grammar of planet formation. The planets are the main sentences. The small bodies are the punctuation, fragments, revisions, and footnotes that reveal how the sentence was written. Without them, the story would be much poorer. We would know the final architecture, but not the discarded materials. We would see planets, but not the debris disk that made them. We would know Earth has oceans, but less about how volatiles moved through the early solar system. We would know meteor showers as lights, but not as trails of comet dust. We would see the sky, but miss the archive. Comets make the solar system feel unfinished. Not unfinished because the planets are still forming in the old way, but unfinished because material continues moving between reservoirs. Dust falls. Small bodies collide. Some objects are ejected. Some are captured. Some return. Some are discovered only once and never again. The solar system is old, but not frozen. That is why the calmest way to end a comet story is not with finality. It is with motion, a nucleus moving outward after perihelion, a dust trail left behind, an Oort Cloud object beginning a million-year fall, a future spacecraft waiting at L2, a survey telescope scanning the sky again, and somewhere beyond Neptune, countless dark bodies still carrying the first chemistry of the Sun. And perhaps that is the most useful way to think of them, not as exceptions to the order of the sky, but as part of that order at its most revealing. The planets show stability. Comets show movement between stability and disruption. The planets show what survived as worlds. Comets show what survived as remnants. The planets are familiar because they remain. Comets are memorable because they return briefly and then disappear. Together, they make the solar system more complete. Not a clockwork of finished spheres, but a living dynamical system with reservoirs, leftovers, exchanges, and surprises. A comet's brightness fades, but the questions it raises do not. Where exactly did it form? How much of its ice is original? How much has sunlight changed? What does its chemistry say about the disk that made the planets? How many similar bodies orbit other stars? How many have been ejected into interstellar space? How much of Earth's early chemistry came from objects like this? A single comet cannot answer all of that, but each comet adds one more measurement to the map. That is enough for a quiet kind of wonder. Not every mystery in astronomy has to be distant galaxies or black holes. Sometimes the mystery is a dark object only a few kilometers wide, almost invisible until sunlight touches it, carrying a record older than biology, older than oceans, older than Earth as a habitable world. Comets make deep time visible for a little while, and because they appear suddenly, unpredictably, and beautifully, they remind us that the solar system still has the power to surprise. The sky is not only a map of fixed points and known cycles. It is also a place where ancient fragments can return, brighten, and briefly make the history of the planets visible to the naked eye. That is why they still matter today. And we leave them there, ancient wanderers returning from the cold, carrying the early solar system briefly into light. Good night.